Okay, it's 12 o'clock. I'm just going to give everyone a few minutes to kind of jump on. Hopefully, my internet stream holds up. Keep your fingers crossed. All right, well, let's get this show on the road. Welcome, tech artists and tech art fans. It's Friday, and it's time for another episode of Tech Art Talk Live. I'm Chris. I'm going to be your host for today's session. And last week, we started talking about linear algebra. And we talked about some vectors, we talked about some matrices, but I'm not really too sure. Everyone just says, okay, cool, it's a vector, that's a matrix. Yeah, you can identify a color as a vector. Okay, these matrices, I have no idea what it's good for. All right, so I thought about it. I said, okay, what we need to do is express how these vectors and these matrices are really so important and why they're so essential for computer graphics. And they really are. And going over my notes today, I realized, okay, I got to give them enough groovy content to keep good. But this is, going to be a really long lecture. So it wasn't my idea, but I'm going to have to break this one up into two more additional lectures today and next week in order to cover everything. And so today we are going to go over transformations part A. And so let me go. I'm going to go ahead and get things started off here. All right. So welcome to Transformations Part A, which is the reason why we're creating all of this linear algebra stuff in the first place. All right. So there we go. We should be ready to boogie woogie. Okay. Let's see. Hopefully, let me get double check. Okay, I think everything is going okay. Yeah, everything looks fine. All right. See, let me say, oh, you don't see my little icon here. Let me get me going here. Okay. All right. Do we see me on here? Hello. Where's my video? Okay, get that. All right. Okay, there I am. Okay. I thought you guys actually might have missed me there. I wasn't really afraid of that, but who knows? Okay, cool. So great. What are all these linear algebra good for? And it all has to do with transformations. So transforming one object from one shape space to another. This is all this is about. You're going, huh? What are you talking about? What's the big idea? Transformations from one shape space to another? Yeah, I'm going to have to explain. It's from one object space to another, one color space to another, one frame of reference to another. So it's all about going from point A to point B. Now, whether you're going from color to color, you're going from object to object, you're going to location to location, even rotation to rotation, it all has to do with transformations. So just for an example here, let's assume that we have a point in space. Now, a point can be defined as a vector in 3D space, right? We identified this last week that a point A can be identified as a vector where you have the x, y, z, and the w component all listed right here in a column. And so here we have this point in space. It's got its x, y, z components in here. Okay, the w for this is assumed to be 1. Because this is not a direction, this is a point in space, we're assuming that we have the x component, the y component, and the z component, and 1 listed up here and there. So that's the definition of a point in space. Okay. Now, then you're going to say, what's with this W business again? Well, this W business is all about homogeneous coordinate systems. And the homogeneous coordinate systems, without going into too much linear algebra here, it allows the translation to be performed in conjunction with rotations and scales. And you're going, huh? You might be raising your eyebrow. What's the big dealio? And once again, if W is a value of 1, that means that we're dealing with a point, and if it's 0, then we're dealing with a orientation or a direction. Okay, ultimately, when we multiply this vector or this point against a 4 by 4 matrix, then all of the translations get nullified out. And we'll get into that in just a little bit. So what are we talking about here? Okay, we already defined that we got a point here. And then we've got this transformation matrix, T. What do we call it? We'll call this T matrix. And it's a 4 by 4 matrix. So there's 4 rows and 4 columns. And so ultimately, the big formula that we're going on here, ultimately, this is one reason why linear algebra is so important, is that A prime, or the point, or A equals the transformation matrix times the original point. And going, huh? Really? Really? That's all that's going on here? Yep, that's all that's really going on here. You've got the transformation matrix times the original point, gives you a brand new point, gives the new frame of reference. Okay. So let's go on for the basic case, the translation. So what we want to do is translate an object from point A to point B. Easy enough. So it's got a translational value in the x component, y, and the z component. So it's going to move in a little bit of x, a little bit of y, and a little bit of z. And so you create your translation matrix that looks like this. You've got the identity matrix going down the horizontal, going down the diagonal. And then you've got, down this last column, you've got the x, the y, and the z components, and then followed by 1. So here's that 1 again. Start to notice some kind of familiarity. Okay, so what good is this? So I'm going to bring up some Houdini. And so look at this. We've got Roberto here. We've got Roberto, our hero here. And so what we're going to do is I'm going to go in here and I'm going to create a translation matrix. And I've got this little icon here that designates it here. Notice that we wanted to move, I want to create a translation matrix that moves, let's see, 5 in x, 0 in y, and 5 in z. Then according to that formula that I had just given you, we're going to create the identity matrix here. And then 5 is the x component, 0 is the y component, and 5 is the z component. And of course, we have 1 in here for the w component here. And so this is the translation matrix. Now, watch what happens when I actually multiply this transformation matrix against Roberto. Well, actually, not only against Roberto, but Roberto is, how many points does Roberto have? Okay, Roberto's got a lot of points. Roberto has about 20,000 points. So for every one of Roberto's 20,000 points, I'm going to multiply each one of those points against the translation matrix. And when I do, I get this. And then I'm going to fan out. Oops, I forgot to turn it on. There it is. There's my Roberto. You say, okay, Roberto hasn't changed any. Well, no, he actually has, because the original Roberto was way over there at the origin. Now what we did was we multiplied every single point in Roberto by this 4 by 4 matrix. This is the new translation matrix. And what he did was he translated from point here to point there. Okay, so you get it now? So this transformation matrix transformed Roberto from the origin to this new location. Okay, so that's how we translate. What do you got to do if, that's an easy case. What's even easier is scaling. So you take your x component, and then your y component, and then your z component, and instead of leaving the identity matrix going down the diagonal, you will put your x, y, and z components right in there, and then you multiply that against your original point. So let's take a look to see how that works with Roberto here. Okay, we've got Roberto. He's sitting up there. Everything is copacetic. Everything is fine. Let me see if I can focus in on Roberto. All right, so I've got my scale matrix here. I've got this identified just here, and I wanted to scale it 2 in X, 3 in Y, 4 in Z. And so I created my rotation, my scale matrix with 2, 3, and 4 going down the diagonal. And notice here again that 1 is in place so that we can get the multiplication right. Now, when we multiply every single point in Roberto against my scale matrix, this is what I get. I'm going to go ahead and turn this on. Whoa. And then we see Roberto has scaled dramatically. He's scaled 2 times in X, which means he's twice as wide, 3 times as tall, and 4 times in the Z. So Roberto is really stretched here. But you know that he is stretched because he was the little guy over here. But now, after we applied the scale on Roberto, we get this big boy here. Okay, now translation and scale were pretty easy. You know, not a problem. But I'm afraid that's where things stop being easy and start getting kind of ugly. Because when we get into rotations, it's 3 different rotations. That means you got to create for the X direction, the Y direction, and the Z direction. And they are different, of course. So you've got some kind of angle that you want to rotate around the x-axis, right? Okay, the x rotation matrix is 1 on this corner and 1 on this corner, and inside of the rest of these is cosine of the angle minus sine of the angle, and then cosine of the angle. The y matrix is kind of similar, but they kind of change up the order on things. There's cosine of the angle at this corner and 1 at this corner, but over here there's sine of this angle, there's the minus sine, and then there's the cosine. And then the z is, once again, something similar, but here that moves the values over here. Now, if you really want to go into this, you could go ahead and prove all of these matrices yourself. It's kind of a exhaustive exercise, but this is a short tech art talk, so we wanted to try to get things going. And there is an assumption is that we want to assume that this is all right-handed coordinate space. In other words, is that when we say that we are rotating in the x direction, let's see, this is my right hand. Okay, so I'm going to have to move this over here. So if we're rotating in the x direction, it's good for well, needless to say, rotating in the x direction, the y direction, and then the z direction, right? Okay, cool. So let's see what this actually looks like. All right, I'm going to turn off my scale rotator. So we've got Roberto here. And so what I had to do is create 3 rotation matrices. My first rotation matrix, we're going to rotate just a little bit here. And let's see how we're going to rotate this guy. We're going to rotate him 45 degrees in the x-axis. Okay, here is my rotation matrix. We applied that formula, 45 cosine and 45 sine. They're going to be the same, you know, because that's kind of like the magic of sine and cosine. But anyway, we've got 0.71 minus 0.71, 0.71, and 0.71 in here. Okay, cool. Now what happens when we take Roberto and then we multiply Roberto by this x rotation matrix? We get Roberto, but rotated in the x direction 45 degrees. Okay, not a problem. Similarly, we could do the same. We've got Roberto, and we're going to rotate in the y-axis. And we're going to rotate in the y-axis 60 degrees. So we're going to rotate Roberto 60 degrees. And these are our corresponding sine and cosine values. So once we rotate Roberto 60 degrees, this is what we get. So Roberto has just been rotated 60 degrees. Piece of cake, right? All right, now let's do it with the z-axis. We're going to take our z-axis. We're going to rotate around the z-axis 45 degrees. And here's our sines and cosine values put inside the matrix. So this is what my Z matrix looks like. Okay, let's see what Roberto looks like when we've got the Z axis. Okay, we rotated Roberto along the Z axis 45 degrees. All right, now we have a whole bunch of transformations. Now, whenever you go into Maya, whenever you go into Houdini or any other package, Blender, 3D Studio Max, it doesn't really matter. They're all going to be doing the exact same operation. This is what's going on inside of your model every single time you do any kind of operation. It's this exact same stuff going on every single time, without a doubt. Every single software ever created in the world that does 3D manipulation is doing these exact steps that we're going through here. Now you're probably going, well, okay, that's really extensive. And that's kind of like, well, in the old days, like people don't remember this, but in the early days of silicon graphics, it really did take about 5 to 10 seconds to rotate an object. It did take that long. And things really were slow. But GPUs have gotten fast, and things have really gotten super fast. So if we wanted to apply all of these transformations to Roberto, what are we going to have to do? Well, we're going to have to apply the translation first, and well, actually, we're going to have to go and probably what I would do is I'd probably scale Roberto first. Oh, I'd probably scale him first, right? So this is my scale. So I'd scale him first, and then I'd do all of my rotations. And then once I'm finished with that, then I would do all my scales. And so this is a lot of operations. You're saying like every time I got to go and move my character around, I got to first scale him, and then I got to rotate them in the X direction, Y direction, the Z directions, and then finally translate. But the early mathematicians who created linear algebra came up with something to kind of facilitate things. Instead of multiplying each point individually against each matrix, all of the matrices can be kind of collapsed on top of each other. That means if you multiply one matrix against another matrix, that combined product is the same as actually doing the first matrix and then the second matrix. So in other words, all you have to do is take all of these matrices and then add them up, multiply them against each other, and then you end up with just one matrix. But the caveat to this is that the order is super, super important, and it's not commutative, which means is you can't change the order around. The order is super duper really important. And so if you're going to deal with the way that like Maya or Blender deals with things, now Houdini's a little different. Houdini allows you to go ahead and muck with the order on things, which is really cool. But Houdini, UE4, Unity, they don't allow you to do this. What they do is they follow this thing. It's called post multiplication. And so in other words, in order to create this final matrix, what they do is they take the identity matrix, multiply it by the translation, and then the rotation of Z, Y, R, S, and then multiply it finally by A, and then what you end up with is one final matrix, and then you multiply it by A, and then you go like, and this is called, do it in post-multiply. Now you could do it pre-multiply when you change the order around, but this is the kind of the way that OpenGL does things. And kind of if OpenGL does it, then I guess we should follow along with it just as well. All right, so let's go ahead and multiply this around. So we've got these, so we've got all these orders. So what are we going to do first? Well, I'm going to lay down a matrix. Yes, this is a homebrew digital asset that I created on my own. Yes, so I'm going to go ahead and follow that order. Now, I don't have an identity matrix, but so I'm going to start with just the translation matrix, and then I'm going to toss in the what is the order on that I wanted to follow? I'm going to get the Z rotation, and then I'm going to get my Y rotation, and then I'm going to get my X rotation and put that in there. Then I'm going to get my scale. All right. So what I'm doing is I'm concatenating all of these matrices against each other. So I'm getting, basically, I'm taking my scale and then multiplying it by my x rotation, my y rotation, my z rotation, then finally multiplying it by my translation rotation. My translation. It's not a translation. And what does this ugly thing look like? Well, if we look over here, if we go over here to the operation, and this is the concatenation, and so what does this actually look like? Okay, so it is not behaving, transform, okay, refresh, okay. Okay, it's not showing up. Okay, regretfully, I'm having a technical difficulty. I'm doing something wrong, and uh, it is just not concatenating. Why aren't you working? I do not know. Okay, but what we can do is then take the final product of this, and then what we're going to do is I'm going to multiply this against Roberto here, and then what we have here is an untransformed Roberto. Oh, having a technical failure here. How embarrassing. This is not fun. Okay, so I'm going to turn off my Roberto here, and we are not going. Okay, come on, refresh for me. Give me a transform for me, please. All right, so actually I did have a fallback in case something did actually fall, happen to call, did happen to that. So what I did was I reproduced all of these. Here's my rotations and my scale rotation, and then here is, I'm going to go and multiply them right here on this node. And there is my Roberto that is now rotated a whole bunch of degrees. He's scaled a whole bunch of different directions, and he's been translated 5 units in X and 5 units in Z. So Roberto started off as this little guy over there, and then once we applied our transformation matrices, this is what he looks like, this big guy. All right, so thank you very much for your patience looking at these world space. We're going to call this world space transformation. So what this is actually a preview into what we're going into next week, because this is much larger, part of a much larger pipeline. So what we're doing is we're transforming our object around. We're moving him around. We're transforming it from here to there. We're doing some rotations and some scales. But that's all we're doing. But that's only part of a much larger uh, um, this is only part of a much larger scheme. What it's actually dealing with is the full transformation pipeline. And the full transformation pipeline is what we are going to be dealing with next week. So call in, pull in next week, and then we will go over the full transformation pipeline of the object, because what we see here is our Roberto is, he's in 3D here. But if you remember, a computer monitor is 2D. So what do we do in order to do this? Well, we have to go through the full transformation pipeline. Okay, and computer monitor is frozen. Okay, having a lot of technical difficulties today. Well, thank you. Tune in next week, the rest of our discussion of our transformation matrices, and I promise you will have a little blue pill, red pill moment there where you're really going to say, like, okay, so this is going on all the time. I don't believe it. Well, this is exactly what's going on every single time you move anything in any 3D software. If you like what you saw, subscribe to my YouTube channel. Check me out on Facebook. That's Chris Rhoda. And there is a TechArt EDU on page on Facebook as well. And if you want, check me out on LinkedIn. That's Chris Rhoda as well. Thank you very much for your time. Have a great week, and then I will see you next week on TechArt Talk Live with part B of our transformation. Have a great week.